Now we verify that the de Broglie waves are responsible for the findings of the Davisson and Germer experiment. In the last video, we have seen when the Davisson and Germer conducted this experiment for different accelerating voltages or for different energies of the electron beam. A maximum is obtained at an energy of 54 electron volt at an angle of 50 degree between the incident beam and the scattered beam. Davisson and Germer originally conducted this experiment using this nickel crystal. Okay, so the nickel crystal, the atomic planes are the parallel planes. The spacing between the different planes, spacing d, that is equal to 0.091 nanometer, and this angle is 50 degree. Then angle 65, that is the angle between the plane and the incident beam. Okay, the Bragg plane, the crystal plane, and the incident beam, that is 65 degree. Okay, so this is the situation here. 54 electron volt electron beam comes in, and we get maximum intensity at an angle of 50 degree, which corresponds to an angle of incidence 65 degree. Okay, so with that idea in our mind, we see for nickel the spacing, as we said earlier, it is 0.091 nanometer. There is intense reflection at phi equal to 50 degree. The angle of incidence theta, okay, relative to the Bragg plane, that is calculated as 180 minus 50 by 2. Okay, so 50, we know it is this angle 50 here, and 180 is the angle from this point to this point in the plane. Okay, so we subtract the 50 from 180, then divide it by 2, because this angle of incidence here, this is the angle of incidence, that will be equal to the angle of reflection, the angle made by scattered beam with the Bragg plane. So we get theta is equal to 65 degree. Then the Bragg equation for maxima, in the case of the diffraction, is n lambda equal to 2d sine theta, where n is the order. We take n as equal to 1. So lambda is equal to 2, d is 0.091 into 10 raised to minus 9 sine 65, which is equal to 0.165 nanometer. So lambda is equal to 0.165 nanometer. So if we use the Bragg's equation for the diffraction maxima, we get the wavelength of the wave associated with the electron as equal to 0.165 nanometer. Now we calculate the expected wavelength of the electrons using de Broglie formula. Okay, now since the electron kinetic energy is 54 electron volt, we know when we compare it with the rest mass energy, the rest mass energy is 0.51 mega electron volt. When we compare with it, we get this as this is much less. 54 electron volt is much less compared with the rest mass energy. So we use the non-relativistic calculation. Okay, we can safely use non-relativistic calculation. The kinetic energy is equal to E square by 2m, P equal to 2 root 2m kinetic energy. So that is root 2m is 9.1 into 10 raised to minus 31. 54 into 1.6 into 10 raised to minus 19, that is equal to 4 into 10 raised to minus 24 kilogram meter per second. So this is the the momentum of the electron. Now we calculate the de Broglie wavelength. De Broglie wavelength lambda equal to h by mv, that is equal to this, that is 0.166 nanometer. So now if we use the de Broglie equation and as we calculate the wavelength, we get lambda is equal to 0.166 nanometer. Earlier, as we calculated the wavelength of the electron using the Bragg equation, we are getting 0.165 nanometer. So the two results are agreeing. Okay, they very well agree. So the Davisson Germer experiment thus very clearly, directly verifies the de Broglie hypothesis of the wave nature of the moving bodies. So electrons definitely is behaving like a wave. That is clearly established. Okay, so the importance of the Davisson Germer experiment is it directly verifies the de Broglie hypothesis of the wave nature of the moving bodies.